Hey, we got Brendan Harvey with us this morning.
Yes,
That's,
sir. Did we have homework due on Sunday?
uh, I think I, I think I goofed up on the homework there, Brendan.
Okay, because I could not find a place to submit it because I did it. But
Yeah. When I goof up, what it means is you guys get an automatic 4.
hey, I'll take it. Still some
Well,
good practice though. But
I think
this
I goofed
technology
up.
is great until it doesn't work, right?
Yeah. Well, part of the problem is technology, and part of the problem is people screw up. But
Yep, humans,
but
right?
we're going to make it right. Now let me get my picture on here, maybe. Yeah, here we go. Yeah, there we go. Yeah, good deal. Now, is that you, Brendan, that I'm looking at with the mustache? Uh-oh, we need some sound. I need some
Sorry, I
sound.
was muted. I forget.
Oh, there you
Yep,
go.
that's me.
You're on. You're on. Hi. Nice mustache there, Brendan. And we also have some other wonderful students. Let's see. We got Darren, Brendan, Ashley, Nicholas, and Ben, and maybe some others here. Maybe that's all for right now. Okay, well, mute all it says, but allow participants to unmute themselves. Okay, that's good. And we have Nicholas. I don't see his picture there, but he's on here. Good deal, Nicholas. Ashley. See who else we got here. I guess that's it. Okay, well, I wonder if this board is showing up. Maybe I need to adjust this thing. Let's see. Hang on a minute here. Oh, yeah, I think I'm down too low. What if I move this? Yeah, that's not too bad. Yeah, there we go. Tuesday, September 8th. All right, well, let me see where we are here. These holidays can sort of throw us out of step a little bit. But like I was explaining to my friend Brendan there, I think I screwed up on the homework assignment somehow. And when I screw up, you guys get an automatic 4 on your homework. But I still would like for you to be able to work what I intended for you to do. So let me go back. Let's see. This is the 8th of September. And the last time, what I wanted on homework number 6, I think this is the one that caused trouble. And I think what I wanted was problem 221 on page 81. But I think what happened is it came out to be problem 81. Well, there is no problem 81. And so some of you had trouble finding that because it's not there. We could work it together. That'd be fun. But on that homework problem number 6, it looks like since I screwed up, everybody gets a 4 on that one. So do not worry about that one. Now today is, I think this one's going to be okay. This is homework number 7. And I believe this is problem 226 on page 82. Now, is that right? Is that what we have here? Yeah, well, it is screwed up. It says chapter 2, problem 2 on this thing here. But maybe I could put that on an announcement so that you would have it. But see, it's not due to until the 11th. This is due the 11th, which is what? Friday? Yeah, I think that's Friday. So I think that's a legitimate one, even though it's screwed up on the schedule. It says problem 2. What I wanted was 226. So let me make a note to put that in case somebody didn't watch the video here. I'm going to put that in the announcements. And then it will be okay.
Are you planning
go?
on,
Go ahead.
Professor Griffin, are you planning on revising the schedule, you know, going through and,
Yeah, I need to change that, but it shouldn't affect us too bad. I think the rest of it's okay.
well, I can see right now that on the September 15th, the homework is wrong too.
Oh, really?
Yeah.
Let me look at that. September 15th. It says problem 83, doesn't it? I bet that's a screw up. Okay, now let me get that right. Okay, now just a minute here. You're absolutely right. And so we're going to fix that. Actually, that's homework problem 9. That's a ways down the road there. Well, I'll revise that and fix that. Now, who just told me that? Who was that I talked to?
Nick?
Was that Nick? Yeah, thank you, Nick. And I'll fix that. Good deal. I think Nick's in my, aren't you in my physics class, Nick?
I got you for a couple classes.
Good for you. Okay, well, maybe we could get started today. I wanted to do some more today on strain. Yeah, strain. And maybe some review, because you are going to have your first test next week. I think your test is the 15th. Yeah, I'll give it to you, the 15th. That, you know what that is? That's a week from today, isn't it? Yeah. But I gave you 3 days to do these tests, so you shouldn't be pressured too badly. Well, unless you have a comment or question, we're going to launch into some exciting problems here. And I wanted you to do that one. We probably should do that one, since I screwed up on that. Let me see what that is. Oh, nasty little problem. But I bet we can do that. That looks pretty easy. We did one very similar to it, I think, recently. But here, we're going to do this right now. Here we go. If you wanted the strain along the x-axis, what you do is you take your final length and you subtract your initial length. And then you divide by your initial length. That's what strain is. Well, in this case here, it's a square, and it got shorter. Here, I'll draw you a picture. It's a square. That's more like a rectangle, isn't it? But we'll make it more like a square. It's a square, and it got shorter. And what it did was it got shorter. On the x-axis, anyway. It got shorter, and it got shorter by, I'm on page 81 here. We're doing some of the homework that I wanted you to do. Make sure you know how to do it. It looks like the final length is 20 minus 0.6. What's 20 minus 0.6? 19.4? And the initial length was 20 inches. And if you divide by 20 inches, well, that's pretty easy. I can do that. So the answer is going to be negative. That means it got shorter. Well, I got a normal strain in the x direction of 0.03 nothings. Well, let me see if that's what the answer book says. I was just doing 221 because that's what I wanted you guys to make sure you can do that. Let me see what they said. 221, they said minus 0.03. Uh-oh, I forgot my minus sign. I told you it was, well, obviously it's minus, and that means it's getting shorter. Hey, we got that right, except I forgot my minus sign. Now, if you wanted the strain, it's a little Greek letter epsilon in the y direction. Well, it got longer. Okay, well, how much longer? Well, I don't know. Looks like it got longer by 0.2 at the top, 0.2 at the bottom. That makes 0.4. So that's going to be 20.4 minus 20 over 20. Here we go. We're going to get the strain in the y direction. Okay. Should be able to do that in my head. In my head, I'm getting 0.02, but that might not be right. Let me make sure. Let's see, 0.4, and you divide by 20. Yeah, I got it right. See, even a blind squirrel finds a nut now and then. Ta-da, and it's plus this time. Now, sometimes books will go inches per inch, but you don't have to. You can just do nothings. Well, let's see what the answer book says. To 221, yeah, 0.02, and they did win. They went inches per inch. Only they don't put their units in brackets like I like. Let me tell you why I like that. Uh, I'm going to erase all this stuff and we're going to have some fun. But first, did you have any questions on any of that? Automatic 4 for everybody on this because I screwed up on that homework assignment. And thanks to one of my excellent students, I think I wrote it down. There's one that I need to repair. Okay, here was your chance to ask me something. Nobody said anything. Are you sure you don't have a question? Okay, well, I want to spend just a couple of minutes on this business about why I like brackets on my units. See, there's names of things. Come on now. There we go. There's names of things. There's symbols for things. And there's units for these quantities that we study. Like, for instance, normal stress. Normal stress, we have a symbol. It's that little Greek letter sigma. So lowercase sigma. Okay. And the unit for that, well, see, what's confusing is there's the American customary unit, and there's the SI, or used to be a metric unit. The American customary unit is the PSI. But the System International unit is usually they're in kilo, or maybe even megapascals. They could very easily be in megapascals. And instead of PSI, they might be in KSI, or even in MSI. Okay, well, let me give you some others here. There's torque. Now, instead of me boring you guys out of your gourd, I'll leave these blank and I'll let you fill them in. I'll give you, I don't know, a couple of minutes I'll give you 2 or 3 minutes and let you fill those in. That's enough. I just wanted to hit the highlights there. Okay, I'm going to shut up for 2 minutes, and I want you to fill these in. Okay. On your mark, get set, go. Fill those in. Well, I don't know if that was 2 minutes, but I bet you're done by now. The symbol for torque that this book uses is T. And the units are Newton meters. Now, wait a minute. Yeah. No. In the American customary, I'm doing the wrong one here. In the American customary, it's foot-pounds. There you go. But in the SI, it's Newton meters. Okay. Deformation. You might have forgot that, but it's a little Greek lowercase delta. Remember the uppercase delta is a deal like that. But this is a lowercase delta. And the American unit would just be feet, or it could be inches. You could have inches or feet. And in SI, it's in, well, it'd be in meters, or usually it's more like millimeters. In fact, this is usually in inches. But if you had meters, that'd be okay. Now, shear strain, that's that funny looking lowercase gamma. It's a Greek letter. And in American customary, well, it's nothings. And in SI, it's nothings. Now, some books might put inches per inch. And our book sometimes will put radians. But see, a radian is dimensionless. So you could just leave it dimensionless. And so is this one here. It's dimensionless, only some books will put inches, no, wait a minute, millimeters per millimeter, maybe. How'd you do on that? Any question on any of that? Okay, well, let me show you. I got room there for two more. Let's talk about mass. Well, the symbol for mass is M, right? Yeah, they use a little m for mass. And in this system here, it's the well, actually, I don't know if we've mentioned this, but it's the slug. And in this system here, it's the kilogram. Wait a minute, I'm forgetting my my brackets. And let's do one more. Let's do distance. Does that show up on there? Yeah, pretty much. They use a lot of symbols for distance. They use, well, even deformation is a distance. So they use the delta. They use L sometimes. Maybe a little letter D. Sometimes they'll go delta X or delta Y or delta Z, or they'll have a little S. They use a bunch of symbols for distance. Now in the American, it'd be feet. Well, it could be inches, like it is up here. And in the metric system, it's M. Now, I want you to notice something. There's an M here and there's an M here, and they are very, very different. This M is the symbol. It's an algebraic symbol. Algebraic. It's an algebraic symbol. But see, this M here, that's a unit. That's a meter. And I don't want you to get confused. There's names, there's algebraic symbols, and there are units. Do not get them confused. And the brackets help me to keep me from getting confused. Because I look at that M there and I think, oh, that must be mass. See that little M kind of looks like mass. Well, it's not. Because of the brackets, it's meters. Okay, there's a little review there. Maybe you didn't need that, but maybe you did. Any comments or questions on that? Okay, well, let's do something else. Here goes. Get rid of all that stuff. By the way, there was a lot of other things I could have put on there. Maybe 1,000 other items I could have stuck on there, but that was enough to kind of give you the feel for that. I put some of the more important items in our course. In other courses, you would have lots of other different things. Like in electricity, you could have volts, for example, or current. We don't need to worry about that in this class. Okay, well, let's practice a strain for a minute now. Let me find what I want to do here. We're going to do a problem with strain. All right. Unless you had something that's bugging you that you wanted me to do, I'm going to do a problem with strain. All right, nobody said anything. We're going to have one of our old faithful 3, 4, 5 triangles now. Well, this is a 3, 4, 5 rectangle. I didn't make it quite long enough, I don't think. So let me doctor this up a little bit. You know, I could measure this. I'm too lazy. I won't. I'll just make it a little longer. I can tell it needs to be just a little bit longer. All right, that's pretty good. There's a 4 meters and 3 meters. How about ABCD? That sounds good. So the diagonals would be 5 meters. All right. Now let's deform that. And I'll show you what it's going to do here. That's C right there. Suppose this comes over 3 and up 3, like that. Comes over 3 and up 3, like that. And suppose this goes up 2 and over 2, about like that. And now we're talking centimeters now. Okay. And suppose this goes over 1 and down 1. All right, now here's our new deformed picture now. Okay, now this corner C, now this, you could call it C prime maybe. See, it's moved over 3 and up 3. This corner D here, call it D prime. It's moved over 2 and up 2. In this corner B, you could call it B prime. It's moved down 1 and over 1. And we'll keep A the same. See, A is down here in the corner. Can you tell that A used to be 90 degrees? A used to be 90 degrees, but now it's going to be a little bit more, isn't it? Does that make sense? A is going to, that corner down at A is going to be a little bit more. And you know the rule for finding the shear strain at A, you go pi over 2 and you subtract this angle here. Pi over 2 minus theta. See, that theta is bigger than 90, isn't it? And it has to be in radians. Let's take out a minute here. I'll give you guys a minute, and I'm going to see if you can find, see if you can find this new angle theta down here in the corner. It's bigger than 90. And see if you can find it in radians. I'll shut up for just a minute, and I'll let you see if you can find it. Go ahead. Well, I don't know if that was enough time. but I found the angle in radians and also in degrees. In degrees, it comes out to be a little bigger than 90. I'm getting 90.5522 something degrees. And in radians, I'm getting 1.57991 radians. Now, if anybody need help with that? Let me go to one of my excellent students here. We'll pick on my friend, having trouble making this thing move down here. Dang it. Yeah, there we go. Shane, unmute. Did you have any trouble getting those, Shane?
No, I got the same answer.
Yay, good for you. Mohammed, how'd you do? Did you get those, Mohammed?
No, actually, I got something different. Can you show me how did you do that?
We better do it. That might be a good idea. Okay, now do you remember the last time I was with you guys? I told you that the tangent of an angle, if it's small enough, and these angles are very small down here that I'm talking about. See that little tiny angle there? If an angle is, say, 1 degree or 2, even 2 degrees, the tangent is equal to the sine of the angle, and it's equal to the angle itself if the angle is in radians. I was telling you guys that last time. So we can apply that here. Now, if you wanted the tangent of, see this little tiny angle here at A, goes from A to B, and from A to B prime there. The tangent of that angle, we probably shouldn't call that theta though. Let's give it a different name. How about we call this little bitty angle, say, alpha? There we go. The tangent of that alpha is 1 centimeter divided by, well, let's see, 4 meters is 400 centimeters, right? So it's 401 centimeters. Take 1 centimeter and divide by 401 centimeter, and you will get 0.00249337, blah, 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 blah. That is equal to that angle in radians. Then you can get this little angle here. Why don't we call that beta? We'll give it a name. We'll call it beta. Well, see, the tangent of beta will be 2 centimeters divided by, well, it'd be 302 centimeters, which will give us 0.00662252, blah, blah, blah. And see if you'll add those to this 90 degrees. And remember, 90 degrees is equal to pi, well, it's pi over 2, right? So this angle here, you got pi over 2. And this angle here is equal to pi over 2 plus alpha and beta combined. because it got bigger. Hey, you know what? It's going to come out negative. Can you see that? The pi over 2's cancel. And this thing here called the shear strain at A is going to be negative. Well, you'd have to add those two. So here, let me add those. Plus 0.00249,377. You get negative 0.00911629 nothings. That should be the answer. I wonder if that's right. Let me look and see if that's right. Uh, 0.009116.3. Yeah, yay, we got that right. Mohammed, did that make sense that time?
Yes, sir.
Good. Anybody else have a question on that? Now notice it came out negative. Did I put it? Yeah, I put a negative on it. And what does that mean for shear strain? See, this is called shear strain. It's called shear strain. And if it's negative, that means you've got an obtuse angle. It's an angle bigger than 90. If it's less than 90, they call that an acute angle, and the shear strain is positive. I tell you what, let's do the shear strain maybe at B. That'd be good. Or D. Okay, let's do that. We're going to try to find the shear strain at D. Now, how are we going to do that? That's a good question. Well, to find the shear strain at D, I bet we can do it. You see, what we'd have to do is we would have to find this angle here. See this angle here? It turns out that angle is less than 90. It's less than 90. Okay, but now how would we find that? Well, let me think now. It kind of hurts my brain there to figure that. Now the 90, it used to be 90. This angle here in the corner used to be 90, okay? And then they deformed the thing, and it turns out that that angle should be less than 90. What you'd have to do is you'd have to make a triangle. Come over here. And make a triangle. And that triangle, see, that went up 2 and this went up 3, so it goes up 1. So this angle here, why do we call that? We'll give it a name. We'll call that alpha. I think that goes up 1, and it has a distance of 2. I think it's 405. See, I think it's longer. Yeah, it's 3 longer here and 2 longer there. I think it's 405. And then you need another angle. Now where is that angle? I think it's here. You'd have to come down here. These are very skinny angles. And see, that moved over 2, so that moves over 2. Why don't we call that angle there, that skinny angle beta? I think that's 2 over, well, actually, I think it's 302, isn't it? Yeah. Got longer, it's 302. Not very neat, but basically your normal strain at B is going to be pi over 2, need a little room in here, minus this new angle, which is pi over 2 minus alpha minus beta. Pi over 2 is canceled and you're left with alpha and beta. If you'll add these two up, I think you'll get your shear strain at that corner. Does that make sense? I think it does. And you could solve for that. Let me see what it is. It's going to be positive. I'm getting positive 0.009096 blah 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 blah. It's positive. It's, what's that? That's supposed to be a plus. It's pretty similar to this, but it's a little different. It's a little different because this thing did not deform to a parallelogram. If it deforms to a parallelogram, then your strains at the corners will be equal in magnitude, but opposite in plus or minus. Okay, well, that was fun. Any question on that? We could also do the strain at B and C. We didn't do those, but it's getting too messy now. That's probably enough. Anybody have a comment or question? This business here does not always work. The tangent of theta is not always equal to the sine of theta, and it's not always equal to the angle in radians. It's only true for angles that are, say, less than 2 degrees. And even then, they're slightly off, but you couldn't tell it. And so you can use that to solve for your shear strains. Okay, well, let's do something else then.
Professor Griffin,
Yeah.
this is Samuel. Why did you subtract alpha? And if, like, I mean, it was 90 degrees, and didn't alpha, alpha make it bigger and beta make it smaller? Therefore, shouldn't you be adding alpha and subtracting beta?
Let me see if I can draw, Samuel, what's going on here. You really need to do this on graph paper. But you understand you did have a rectangle to start with. You understand that. But what happened was they deformed it. And this angle up here in the corner was like, I'm going to exaggerate it. I'm exaggerating that angle up in the corner. Now, wait a minute, Samuel. I was thinking that angle is getting smaller. See, I was going to draw you a deal like this. And I was going to say, Samuel, you can tell that that's going to be smaller than 90. But the fact is this has a slight slope going up, doesn't it?
Mm-hmm.
And I might have done this wrong, Samuel. I might have done this wrong. And I'm going to give you a thank you point here in a minute. I still think it comes out to be less than 90. And so our answer will be positive because it's acute. But this angle here we'll call alpha. And this angle here we'll call beta. And Samuel, I think I did those wrong. I think the alpha is equal to the tangent of 2 over 302. I think I got the numbers right. But I think the beta is, and I think I got those numbers right. It's 1 over 40, oh, no, wait a minute. Yeah, it's 1 over 405. I think I got that right. But see, it actually got bigger. And so this angle here is going to be a negative. So you'd subtract, but this one is a positive. Samuel, I think this has to be a positive. And so this answer is wrong. Now, let me do this right. I'm going to do it right. And I'm going to give Samuel a thank you point because I think he's got a point here. 1 divided by 405. See, and 2 negatives make a plus. Minus 2 divided by 302. I need to see what these numbers are. I think this number is bigger than that one. I think the answer at B is it's still negative. It's still negative. I think it's negative 4.153. What about my decimal point? Negative 0.004153. There's Samuel's thank you point. Because see, this angle got bigger, that angle got smaller. And so you have to subtract that angle, but you have to add that one. See, this number is 1 divided by 405. 0.00247, round it off so that you can see. And this is 2 divided by 302. That's 0.00662. See, that number is bigger than that. And so it turns out that that new angle there is actually obtuse. So you gain more than you lost. And so you have, what do they call an obtuse angle? You have a negative You have negative shear strain at A and B. Samuel's on the board. Good going, Samuel. Anybody have a comment or question on that? Okay, well, let's do some more here. We're here to have fun. And we're going to do another shear strain problem. This one's a fundamental problem. I like them because, see, we can look at it in the back of the book, and they're pretty smart. We can check our answer, and we know we're right. On this one here, you're just going to have to trust me that I know what I'm doing. Any last comments or questions? All right, we're going to do another shear strain. Maybe this will click for you. Now remember why we're doing this. In another chapter that we're going to get to, we're going to learn that there's a relationship between shear stress and shear strain. It's a form of Hooke's law, and this thing here is called the modulus of rigidity. And we'll study that. But see, this is shear stress. And shear stress, steel, for example, is very weak compared to some metals in shear stress. Shear stress will cause steel to fracture, whereas normal stress won't. Steel has an amazing ability to stretch under normal stress and not fracture. But it doesn't do so good on shear stress. Like, for instance, a power takeoff, a crankshaft. When you're putting a lot of power on a crankshaft, you're developing shear stress in that crankshaft. And it's steel, and it can cause that crankshaft to have a problem. Okay, now the one I want to work right now is F2-4. Let me see if I can find it. It's on page 77. Have you discovered they love these 3, 4, 5 triangles? We got another one. Okay, well, we'll just do it. Here goes 3, 4, 5 triangles. Now, how am I going to do that with a scale here? I don't know. I'll try it here. Do I have room for this? I don't know if I got enough room for this. Yeah, I got enough room. The question is all of this showing up on your computer screen? Yeah, not too bad. Yeah, this is, well, in meters, it'd be 0.3 meters. It's 300 millimeters. And this would be 0.4 meters. You got a right angle there. And this would be, if it's a 3, 4, 5 triangle, this would be 0.5 meters. This is problem, it's on page 77. It's problem Fundamental problem 2-4. And you've memorized these angles. I could ask anyone in this class what that angle is, and they could tell me. Let me just show you that. I'll show you what a great group. We're going to go. Samuel was very helpful just a minute ago. Samuel, tell us the angle, that angle down there in the corner. Go ahead, Samuel.
Is it 53.13?
Yes, good going. That angle is 53. See, I wanted everybody to memorize that. It's 53.13. And I bet you have this one here memorized too. Let me go to my friend Julian. Julian, unmute and tell us what this angle is here in the corner. Uh-oh. Julian, Earth calling Julian. Come in, Julian. Uh-oh. Maybe Julian took a break. I don't know. Well, anyway, it's 3687 is what it is. I want you to memorize that. This triangle is so important. It's called a 3, 4, 5 triangle. But see, they're going to deform it. They're going to move this over 5 and down 3. So it puts you about here. I need a different color though. Let me try this green. I don't know if it shows up, but we'll try it. Okay, they're going to deform this thing. What they've done is they've come over 5 centimeters. No. 5 millimeters. Maybe I should have left this in millimeter. Let me leave these in millimeters. That was 400 millimeters. We'll just leave them in millimeters. 400 millimeters. This one is 300 millimeters. And of course, this would be 500 millimeters. Okay. Now this came over 5 and down 3. There you go. It went over 5 and down 3 millimeters. All right. And they want to know what? Let me read this. Triangular plate is deformed. I'm doing fundamental problem 2-4. It's on page 77. They want the normal strain along edge BC. Where is that? Okay. Determine the normal strain along edge BC, and I bet we can do that. See what they're after is the normal strain along BC. Well, where's BC? Just a minute here. This is A, B, C. Okay, I see it. All right. And the average shear strain at corner A. Okay, well, let me write that. They want the normal strain on BC and the shear strain at A. Okay, we can do that. Well, how do you do the normal strain on BC? Well, you take the final length going from B to C. Now, let me think about that. That length is, you know what I think it is? I think it's a square root of 405 squared plus 297 squared. See if that makes sense. See, you did have 300 and you subtract 3, so now you have 297. You did have 400, but it got 5 longer, so that makes 405. Yeah, that's it. And then what you do is you subtract the 500, which was the original, divide by 500. Ta-da, and that's it. Okay, we're going to do that. Here goes. And we'll have the normal strength. All right. 405 squared. 405 squared plus 297 squared. But you have to take the square root. Okay. This number here turned out to be 502.2290 millimeters. It's a little longer than 500, you know it? Then you subtract 500, and then you divide by 500. Well, I got 0.00458, rounded off, nothings, because it's strain. Now let's do the shear strain. Here we go. Now, how do you do that? Well, one way to do it is to take the pi over 2 and subtract this new angle here. Why don't we call this new angle theta? That'd be a nice name for it. And you know what that new angle is? It's pi over 2 minus the arctangent. See this little angle here? Why don't we call it alpha? That'd be a nice name for it, alpha. See, alpha is equal to the arctangent of 3 over 405, which is equal to the tangent which is equal to, well, I think it's equal to 3 over 405. Because that's the angle in radians. But see, this would have to be in radians for this to work. It's not in degrees. Here, let me do it in degrees. 3 divided by 405. The arctangent is, if you take the arctangent, this would have to be in radians, you understand. The arctangent of 0.24405 degrees, you'll get this. Here, let me do that. The arctangent of that in degrees is something bad happened. Now, wait a minute, what did I do wrong here? 3 over 405, yeah, that's the tangent. And so alpha is the arctangent. And 3 divided by 405. And then you hit the arctangent button. Yeah, I think I did that right. You get no, alpha is equal to those many degrees. And when you take the tangent of that, what you'll get is 0.0074. I'm probably confusing everybody. But I bet if you took 3 divided by 405, that's what you'll get. You'll get 0.0074074. You see, that's what alpha is. And if you put that alpha in there, let's put it in there. 0.0074074. And we'll get our shear strain. Here it goes. Well, we're done. It's it's positive 0.0074074 nothings. Because it's acute. Can you see this new angle is acute? Okay, let's see how we did. This was problem F24. Go to the back. And we're going to see if we got that. F24. Okay. F24. They said that normal stress is 0.00446. Well, that's not what we got. F24. They said, hey, now they agree with us on this 00741 thing. Yeah. But now wait a minute. They're getting a minus answer. They're getting a minus answer. I don't think that's right. It's not minus. I think they got the right number, but it's not minus, it's positive. This angle here is acute. Can you see it's smaller than 90? And in their answer book, they put a plus right here. It's not plus. That's wrong. It's a negative. Oh, no, wait a minute. Yeah, I think I did that right. Kind of confusing. But now wait a minute, I might have been wrong about this. Let me stare at this a minute. BC, where's BC? Okay. Well, really what I want is B prime C. And you've got 405 and 297. Yeah. And when you take the square root of that, you'll get something. They have 405 and 2. They have the same numbers I have. Well, let me do that. I got 502 point blah blah, and that's what they got. Okay. And then you subtract 500 from it, right? They've got the same exact thing I have. 502.229. Let me do that. 502.229 minus 500 divided by 500. I'm getting 0.00458, and they're not. The book says, I think they got it wrong. The book says 0.00446. You guys do that on your calculator and tell me you don't get 0.004581. Somebody speak up.
I got 0.004458.
Really? Well, let me do it again here. I might have goofed up. Let me try it again. Who was that?
Ben Harris.
Ben? Appreciate it, Ben. Okay, then I take the square root. Uh-huh. And then I subtract 500. Then I divide by 500. The book is right. I don't know what I did. Who knows? Book's usually right. The book is getting 0.00458 something. And what they did is 0.00446. They rounded off. The book was right, and I just made a calculator error on mine. But now back to the shear strain. I'm getting a positive shear strain, same numbers as theirs, but they're getting a. Oh no! Wait a minute. Wait just a minute here.
Doesn't beta come from above A down to?
Yeah, I think.
A'?
I bet the book is right after all. Okay. Now this little angle is 3 divided by 405. I have no doubt that I got that little angle right. But what I'm after is this angle here. That should be 90 minus that angle, because it got smaller. See, that angle it's smaller than 90. Yeah. Okay.
Professor, in the book, it shows the XY coordinates being at A being the origin.
Yes.
But wouldn't it be from the positive Y to the?
Oh, okay. Now, who am I talking to?
Ben Harris.
Ben. Ben, that's the answer. The angle they wanted, Ben, and I'm going to give Ben a thank you point. If X is here and Y is here, then the original angle that we're after is the 90, and it got bigger. Can you see that that angle got bigger? And so we got the right number, but since it got bigger, if it's obtuse, it's a negative. So their answer is correct. It should be a negative. This should be a plus, in other words. The angle got bigger, and so that makes this a minus. And the answer book was right. You know what I was thinking? I was thinking that the y-axis was going down here, but it's not. It's going up there. Thanks to Ben, we got that one figured out. Okay, I got one more to work with you here. I got 10 minutes left. And this one is, see if I can find it, what I wanted to do here. This one's sort of a review problem. Yeah. This one is problem 177. We may not have time to finish it, but we have time to go over how you do our problems in here. Now help me find 177. This is sort of a review thing here. Where's 177? Okay, I'm still having trouble finding 177. No, there it is. Well, we finally, with my students' help, we conquered that one. Now this is a review problem. It's on page 59. is problem 177. And I've told you guys how to do these problems. You make a sketch and you make it to scale. Have we done this problem before? Does anybody know? I don't remember. Well, if I don't remember, you probably don't remember. I don't know. Here we go. I'm going to use centimeters, I guess. I'm using centimeters. Now they've got a 6 and an 8 feet. You know what they've got? They've got themselves another 3, 4, 5 triangle. It's time you memorized. It's time you memorized the 3, 4, 5 triangle. Definitely time. Instead of 3, 4, 5, though, it's 6, 8, 10. And that's 6 feet. Here you've got a smooth pin. Smooth pin. Only A is subjected to double shear, so you have two brackets at A. And they have a 3 kip force on there doing this. And you all know what a kip is. It's 1,000 pounds. Now the first step in doing our problems is to draw a sketch. Oh gee, I'm running out of time. I got time for one other thing. And that is, you look at your whole structure, you know you have a force here at D. This is a rocker. So at D, you can only have a force going up. We don't know what it is yet. And all I've got time to tell you is that you look at your structure, it's a 3-force member. The only other force is down here at A. It's got 3 external forces. And what do you know about 3-force structures? They're either or they're I'm going to go to my friend Jackson. Jackson, this is a 3-force member. We're almost out of time. If you have a 3-force member, they're either or they're Jackson, what are they? Unmute, Jackson. Tell me what happens with a 3-force structure.
I don't remember.
That's okay. That's okay. That's what we're here for. They're either parallel, and these forces are not parallel, or they're what they call concurrent. They all go through the same point, and you have to find that point. Can you see that these 2 forces go through that point right there? C is the concurrent point. And so that means that the force at A has to go through C, but it can't go to the right. I think it's going to the left. I think it's pulling. But you see this line of action, and you can even get that angle there. That angle would be the arctangent of 8/12, whatever that is. But we don't have time to look it up. That's what the angle is at A. And we have the external forces. That's how you begin your problems. Don't forget to look for 3 force members. It tells you a lot about this force. It tells you its angle. It's sad, but we're out of time. And you do have your homework. I think it's correctly stated in the Blackboard. And I will see you on Thursday. It's a deal. I'll see you then. Bye-bye for now.
Bye.
But thank you very much.
Thank you.